Hello, viewers. I'll be right back. I'm going to go take an aspirin. Let's see, how many viewers do we have? Okay, give me one more second, class. I'm a little bit behind. Okay. Hello, class. Good morning. Hope you're all doing well. I'm a little bit disorganized this morning, so I apologize. Hey, Bugs. Okay, so let's go ahead and get started. Why isn't my document camera showing? There it goes. All right, so I'm going to zoom in. All right, so this is AP Physics 1, October 16th, period 4. So this is going to be our last forces lecture today. And the last two lectures were definitely the most difficult forces lectures, so this one's going to be a little bit easier today. And so this lesson is about what I like to call multi-part systems. Okay, let's see if I can focus that a little better. Focus. So a multi-part system is just a system where there's more than one object interacting. Okay. And so a really good example of a multi-part system is something called an Atwood machine. So let me tell you about the Atwood machine. It's named after a guy named Atwood. And what it is you have a pulley. So here's a pulley. Okay. And so, if you don't know what a pulley is, kind of connected to a ceiling or something. And it's basically a wheel that you can put a rope over. Like that. And the Atwood machine has two masses on either end of that rope. Okay. And so just for this example, I'm just going to choose concrete numbers. So let's suppose that this is a 2 kilogram mass and this is a 1 kilogram mass. All right. So that's called an Atwood machine. The masses could be anything. Focus. I guess it just doesn't want to focus today. So because now this rope is going over the pulley and it's connecting the two masses, okay? So the force from a rope is called tension, which is denoted by T, okay? And there's one key fact about tension that you need to know, and that is that the tension at each end of the rope is the same. Okay, the tension at each end of the rope is the same. Oh, there we go. Got some high quality focus there. So the tension in this rope right here is pulling up on the 2 kilogram mass. Okay, and the tension on this end of the rope is pulling up on the 1 kilogram mass with the same tension. Okay, so the tension at each end of the rope is the same. If you have, so basically a rope carries a single amount of tension throughout. If you have multiple ropes, each rope can carry a different amount of tension. Okay, but if you just have one rope, then that's the same tension on either end. So what we want to do with these multi-part systems, okay, is we want to choose a positive sense, okay? So what we're going to do is we're going to choose a positive direction. This is one of the cases I was talking about how we have the ability to choose what the positive direction is. This is a rare instance where we might actually be choosing downward to be positive. Actually, we will be choosing downward to be positive because I know that this 2 kilogram mass is going to fall because it's heavier than the 1 kilogram mass. So I know that the 1 kilogram mass is going to rise, and I know that the 2 kilogram mass is going to fall. So I'm going to choose any motion in this kind of sense, in the clockwise sense, is the positive direction. Okay? So on this side of the pulley, the positive sense is downward. Okay? And on this side of the pulley, the positive sense is upward, because that represents a clockwise rotation of the pulley. Okay? So we're actually going to take the positive direction to be different for each mass. All right. Another important thing is the magnitude of the accelerations of each mass are the same. Okay. Man, I'm tired. So why is that true? Because if the 2 kilogram mass falls 1 meter in 1 second, then the rope is going to pull the 1 kilogram mass up 1 meter in 1 second. You get it? If the 2 kilogram mass falls 3 meters in 1 second, then the 1 kilogram mass rises 1 meter in 1 second. So what that means is they have the same position time graphs, essentially. And if they have the same position time graphs, they have the same velocity time graphs. And if they have the same velocity time graphs, they have the same acceleration. Okay? So the accelerations of each mass is going to be the same. So I'm I'm not going to have, like, for example, A1 and A2. We're just going to have a single acceleration, okay? So let's go ahead and do Newton's second law for each mass, okay? If I just do a free body diagram for each mass, it's really simple. This 2 kilogram mass is going to have an upward tension, and it's going to have mg would be 20 newtons going downward. That's the weight force. Okay. This 1 kilogram mass has an upward tension from the rope, and it has a downward 10 newton weight force. Okay. Now notice how I've drawn these two arrows to have the same length to indicate that it's the same tension. These two are the same. Okay. And notice that the 20 newton downward force is bigger than the tension. Why? Because I know that the 2 kilogram mass is going to accelerate downward, so I had better have more downward force than upward force. Okay. Similarly, the 10 newton force is smaller than the tension, so I had better have, so that indicates that the 1 kilogram mass is going to accelerate upward. So the free body diagrams kind of have to look like this in order to have the system behave as expected. Type it into the chat. I'm going to ask a question to you guys. Type it into the chat if you know why I don't have normal force in the free body diagram. Okay? I'm curious if you know why I don't have normal force. All right? So, I'm going to do Newton's second law for the 2 kilogram mass. Newton's second law, if you will recall, is net force equals ma. Okay? So, the net force on the 2 kilogram mass is going to be down forces minus up forces. So it's going to be 20 minus t. Very good. Have some good answers. So yeah, these blocks aren't resting on a surface. So if in order to have a normal force, you have to be in contact with a surface. So if you're just hanging, sort of dangling above the surface, there's no normal force. Very good. So the net force on the 2 kilogram mass is 20 minus t. Remember, because of I've chosen a positive sense, for this 2 kilogram mass, downward is positive. So the 20 newton downward force is the positive force, and tension is in the negative direction. Okay? And that equals ma. So that equals 2 times a. Okay? Now I do the same thing for the 1 kilogram mass. So for the 1 kilogram mass, because of the positive sense of this problem, for this 1 kilogram mass on the left-hand side, upward is positive. Okay? So I have tension going upward and 10 newtons going downward. So I have tension minus 10 is the net force. And that equals the mass, which is 1 times the acceleration. So I have a Newton's second law for each object in the system. Okay, so there are 2 objects, so I have 2 Newton's second laws. Notice how I don't have a T2 and a T1 because the tensions are the same at each end of the rope. Okay. Also, notice how I don't have an A2 and an A1 because the magnitudes of the acceleration are the same. All right. So this is an example of what in your math class you would call a system of equations, where you have, for example, you could have an equation like 2x plus 3y equals 7 and negative x plus 5y equals 0. Something like that. That would be an example of a system of equations. This system of equation is really, really, really easy to solve. Okay? Here's why. All you have to do if you want to solve this system of equations is add the two equations together. Now, why does that make it so easy? Well, you can see that right here we have negative t, and right here we have plus t. So when you add these two equations together, the two tensions cancel each other out. Okay, so it's really easy to eliminate the tension. All right. So adding those two together, on the left-hand side, I get 20 minus 10 because the tension's canceled out. And then on the right-hand side, I have 2a plus 1a, so that would be 3a. All right. So this becomes really easy to solve. I just subtract them. So I have 10 equals 3a. Dividing both sides by 3 gives 3.3 meters per second squared is the acceleration. Okay? So what that means is that the 1 kilogram block is accelerating up at 3.3 meters per second squared, and the 2 kilogram block is accelerating downward at 3.3 meters per second squared. Okay? Go ahead and type it into the chat if you know. I'm going to ask another question. If you know, once you've found one of the variables in a system of equations, how do you find the other variable? Okay, if you know how to find the other variable. I'll wait a second for someone to answer. By substitution, yeah, that's basically it. So, yeah, what we want to do is we want to plug this equation, or this answer that I found for the acceleration, back into one of the two equations. Either one, it doesn't matter. Okay? And then solve for the tension. So, all right. So we want, and if you are really afraid that you got the answer wrong, you can actually substitute acceleration into both equations, and you should get the same tension no matter what. Okay, so I'm not generally going to do that, but let me just show you how that would work. Okay, if I was extra paranoid that I got the wrong answer, I would say, okay, 20 minus t equals 2 times 3.3. So that's 6.6 is 20 minus t. I add the tension to the other side. I subtract the 6.6. So that gives me 13.3 newtons equals the tension. All right? So if I'm not confident in myself, I could do the exact same thing with the other equation, and I could say, all right, t minus 10 equals 1 times 3.3. All right? Then I add the 10 to the other side, and I get tension equals 13.3 newtons. All right? So I get the same answer no matter, for the tension, no matter which equation I substitute into. And so that is basically proof that I found the right answer. Okay? so I'm not going to do this again because I'm confident enough in solving these problems that I don't think I'm going to make a mistake. But if you are not confident, you can plug it into both. All right. So let's do some more problems. Let's suppose that you have a table. All right. I will practice my Spanish skills and say una mesa. And a floor, which is what? I think it's like un pilo or something like that. All right. And you have a pulley that is on the end of the table. Okay. And you have a dangling, piso, el piso. Thank you. And so you have a mass that is dangling, and you have a mass that is on the table. Okay. And we are going to say that the coefficient of kinetic friction between the table and this mass is 0.3. Okay. This is a 4 kilogram mass. This is a 1 kilogram mass. All right. So let me. I'm just sort of writing a very simplified problem, but we could actually apply this to like a real life situation. Imagine that you are mountaineering or something, and you're tethered to your climbing buddy, and your climbing buddy falls off the edge of the mountain. Okay, and you're trying to arrest their fall, so your friction, basically the friction on this block is slowing or stopping the fall of the 4 kilogram object. One thing about climbing ropes, this is not, we're doing these problems with ropes that are not climbing ropes. Climbing ropes are actually stretchy. At least I've been told. I haven't done rope climbing. I've only done a little bit of bouldering, but you know, the ropes are kind of stretchy. We're assuming that this is a rope that is not stretchy at all, okay? Because a stretchy rope would complicate things. All right. So I'm going to choose a positive sense. So this system is going to move like that. That is the positive sense. So I'm going to choose downward to be positive for the 4 kilogram mass, okay, and rightward to be positive for the 1 kilogram mass, because as the 4 kilogram mass falls, the 1 kilogram mass gets moved to the right, like that, okay? So let me just do a free body diagram of the forces on each block. So for the 1 kilogram, it's a little bit more complicated because the 1 kilogram is on a table. All right. So that means that there's a normal force. They have a 1 kilogram block has a 10 Newton weight force going down. There's a tension force pulling the 1 kilogram mass to the right. Okay. And then because that's the tension force is going to tend to slide the mass to the right. That means we are going to have a kinetic friction force to the left. All right. So that's the free body diagram. Now we know that this 1 kilogram mass is not going to jump off the table. Okay. It's not going to jump off the table. So that means that the normal force has to be the same size as the weight force. Otherwise, there would be a net force in the vertical direction and the box would lift. Okay. So the normal force has to be 10 newtons. And as you know, the normal force allows us to calculate kinetic friction. Okay, so the formula for kinetic friction is mu sub k times normal. So that would be 0.3 times 10. Okay, so that is 3 newtons. So I know that friction is 3 newtons. All right. So now I can go to draw the free body diagram of the 4 kilogram mass. So the 4 kilogram mass has a tension going upward, and it has a weight force that is 4 times 10, or 40 newtons, going downward. And I know that these two tensions have the same size because of the way ropes work. So I'm going to indicate that by giving them both double slash to indicate that they're the same size. It's a double slash though because these two are the same size but not necessarily the same size as the tension, okay? So these two are equal and these two are equal in size, but normal force is not necessarily equal to tension, okay? So now we're going to do Newton's second law. So I will do Newton's second law for the 4 kilogram, and I will do Newton's second law for the 1 kilogram. So I'm going to go ahead and fill out the right-hand side of Newton's second law. And why don't you think about what I should put for an expression for the net force on the left-hand side for each of these masses, okay? So you think about that and type it in the chat if you know the answer, while I take care of the right-hand side. So the right-hand side of Newton's second law is ma, so I know that this is going to be 4a because it's for a 4 kilogram mass, and this is going to be 1a. All right. And furthermore, I know that I'm going to add these two equations together. All right. All right, no one wanted to say what the net force is, so that's okay. So for this 4 kilogram mass, downward is positive because of the positive sense that I've defined. So that means that the net force on the 4 kilogram is 40 minus T. Okay. For the 1 kilogram mass, rightward is positive. So the rightward force is tension, and the leftward force is friction. So it's going to be tension minus 3. All right. So so there you have it. We don't really care. So the purpose of analyzing the up and down forces for the 1 kilogram mass was purely to understand what the friction force was going to be. All right. So that was the only purpose of the of doing the vertical part of this free body diagram. So adding these two together, once again, tension will cancel. And so on the left-hand side, I get 37 newtons. On the right-hand side, I get 4a plus 1a is 5a. Divide both sides by 5. Okay. And I would get, what, 7.4 meters per second squared is the acceleration of the system. So for the 4 kilogram mass, that's going to be a 7.4 meter per second squared acceleration downward. And for the 1 kilogram mass, it's going to be a 7.4 meter per second squared acceleration rightward. So if this were a real mountaineering problem, this is not that much less than the acceleration due to gravity, so you're probably still toast. You're a goner, okay? So there you have it. To get the acceleration, I would then plug this back into the equation. I'm going to plug it into the bottom equation because that one is multiplying a by 1, so I don't have to multiply by 4. So I would have t minus 3 equals 1 times 7.4. I add the 3 to the other side, and I get that the tension is 10.4 newtons. All right. We're going to do one more example. I'm getting text messages from Mr. Hoyle and Mr. Tucker and Miss Rivette right now. It's very distracting. I'm going to take my watch off because the text messages go to my watch. Taking it off. Okay, so let's do a system that has 3 masses. Okay, so this is going to be very similar to this problem, but with 3 masses. So we have una mesa y un piso y dos pulleys on either end of the table. Okay, and we've got 3 masses. Okay, so we've got a dangling mass over here. We've got a dangling mass over here. And those 2 masses are connected by 2 different ropes. So these are 2 different ropes. So that means we're going to have 2 different tensions. So this rope is going to carry a tension T1. And this rope is going to carry a tension T2. All right. I'm going to say that this is a 3 kilogram mass. This is a 2 kilogram mass. This is a 1 kilogram mass. All right. So, obviously this 3 kilogram mass is going to pull the system so that this will be the positive sense. Okay, so that's what I will define as the positive sense of the system. So upward is positive for the 1 kilogram mass, rightward is positive for the 2 kilogram mass, and downward is positive for the 3 kilogram mass. All right. So I'm going to skip just in the interest of time, I'm going to skip the free body diagrams this time, and I'm just going to go straight to Newton's second law. Okay. We're going to write Newton's second law for the 3 kilogram mass. we're going to write it for the 2 kilogram mass, and we're going to write it for the 1 kilogram mass. Okay? For the 3 kilogram mass, it has 30 newtons of gravity pulling it down in the positive direction, and it has tension from the first rope, T1, pulling it up. Remember, 2 ropes means 2 tensions. For the 1 kilogram mass, okay, oh, I forgot to say that this is a frictionless table. So this has mu equals 0. For the 1 kilogram mass, I have T2 pulling it upward in the positive direction and a 10 Newton weight force pulling it down. So it's going to be T2 minus 10. Now the trickiest one is probably the middle mass, the one that's on the table. So we can see that this gravity and normal force are acting up and down. So they don't really play a role in this problem because the 2 kilogram mass is moving side to side. There are 2 side-to-side forces. There's T1 and T2. All right, there's no friction. If there was friction, I would have to have a friction force going to the left to account for the motion. Okay, so the force that's in the positive direction is T1, and the force that's in the negative direction is T2. All right, so I've handled the left-hand side of all of my Newton's second law equations. And now I have to do the right-hand side, which is really easy. It's just going to be, this one's going to be 3a, this is going to be 2a, this is going to be 1a. All 3 of them have the same acceleration because they're all connected by these taut ropes. Okay, if the 3 kilogram one falls 1 meter, the 2 kilogram one moves to the right 1 meter, the 1 kilogram moves up 1 meter. So they all do that in the same amount of time, so they all have the same acceleration. This follows this exact same procedure. So we just add the 3 equations, and we can see that we have negative T1 and plus T1, so those 2 cancel. And then you can see we have negative T2 and plus T2, so those 2 cancel. All right, so what we're going to have on the left-hand side is 30 minus 10, because those are the only 2 things that don't cancel out. On the right-hand side, we're going to have 3a plus 2a plus 1a equals 6a. So 20 equals 6a. Dividing both sides by 6 is going to give us, I didn't do this intentionally, but it's going to be 3.3 meters per second squared, the same answer as the other one we did. To get the tensions, all right, we plug it into each equation. Okay, so so I would probably plug it into the bottom equation here to solve for T2, because I would have T2 minus 10 equals 3.3a, or 3.3, excuse me, times 1. So that tells me that T2 is 13.3 newtons. Okay. Now plugging it into the top equation is going to let me get T1. So 30 minus T1 equals 3 times 3.3. All right, 3 times 3.3 is 10. So that tells me that T1 equals 20 newtons. I don't know if you can see that. All right. So that's how these multi-part system problems work. This is an introduction to multi-part systems. We're only going to spend 1 day on it just in the interest of time. One thing that I do want to mention is that in these multi-part system questions, you can have some confusion where, if I made a really confusing multi-part system problem, it might not be obvious what direction the positive direction is. Similarly, if I wrote a really complicated multi-part system problem with friction, you might not know if the system is actually going to move. It might be static friction or it might be kinetic friction. So you can get all these sort of confusing scenarios where it's like, I don't know if it's actually going to move or not, or I don't know which way it's going to move. And in those cases, what you have to do is you have to basically do trial and error and see if it were this, let's assume that the system is actually moving and that it moves to the right. And then you would have to work out all the math. And if you reach a contradiction, then you know that your assumption was incorrect and you have to go to a different assumption. I just wanted to say that I'm not going to give you that kind of question, so don't worry about it. It's going to be obvious, all right? So for this one, it's obvious that the system is going to move in this sense because the 2 kilograms is heavier than the 1 kilogram. All right, it's going to be something like that where it's very clear cut. All right, so that's my lesson for today.